Welcome to Allen High School's APIB HL1 chemistry class. We are on the last of our videos on acids and bases, and this next question is tricky. So let's take a look at what we have here. I actually liked it. I thought it was a very creative question and helped you understand your chemistry a little bit better. Now, if it were me and I were approaching this question, one of the first things I'd do is identify. What do I have in these beakers? I have a strong acid, which means it's going to go 100% to H plus Cl minus. I have a weak base, which means I'm going to have to deal with a Kb issue if they ask questions about that beaker. And in here, I have a soluble salt. And that means in this beaker, I have NH4 plus Cl minus. I hope you're getting adept at identifying and that you're realizing that ammonium, which we've talked about since pre-AP, is the conjugate base of our ammonia. So that's what we're dealing with. Now, technically, that's our conjugate base, but it's a conjugate base of a strong acid. So we don't care a whole lot about that unless there's silver, lead 2, or mercury 1 present. Now, question A says, determine the pH of the solution in beaker 1. Well, this is a strong acid, so it means that HCl goes 100%. So remember, we can do this a variety of ways. Let me erase that and start fresh. We can use the SSS method if you want, that start, shift, stop. I'm going to use a simple mole road method. I've got this many moles of HCl per 1 liter times I get 1 mole of H plus for every 1 mole of HCl. So that means I also have 0.100 molar H plus present, and now all I have to do is calculate my pH. So pH is equal to minus the log of 0.100, and that is equal to 1 point. Now be careful, 3 sig figs here, you have to go 3 decimal places. In a pH, the number in front is magnitude, not measurement. Now let's go on. Hopefully that was pretty straightforward for you. That's a 1-pointer. So if you think carefully. Now look, it even gives us the reaction in B, so you're not tempted to be making weird reactions. We're given the Kb value. You might want to underline or list your givens. The only reason you're told it's at 25 degrees Celsius is because K values change with temperature. Right? Now, it asks us to first set up the Kb expression. So we have Kb is equal to NH4 plus times OH minus over whoops, I forgot my 4 there, sorry, NH3. Now, we have not added volume to volume. We're dealing with only this beaker, so there's no dilution, there's no stoichiometry. This is, as if you read carefully and pay attention, a straightforward rice problem. Whoops, I don't know why I wrote H2O, there, H2O, NH4 plus OH minus. Don't care much about that water. There's not a common ion. We've not had another source of NH4 plus, nor do we have another source of OH minus. In the beaker, we have 0.100 molar of this minus B. Remember, you want to use B as your reminder if you're asked for pH, that it's 2 steps. Now in this case, we're not asked for pH. We're asked for simply the OH minus. 0.100 minus B, B, and B. They give us our K value, so now we can substitute in. 1.8 times 10 to the minus 5 is B squared over 0.100. I neglected that because this number is greater than 100 times my Kb. which means that it doesn't ionize very much, that the percent ionization is quite small. Right? So if you solve this, you should get that B, which remember is equal to, in this case, your OH minus. Redefine what your symbols mean, and that is 1.3 times 10 to the minus 3 molar. Okay? So this would have been worth a point. You would have earned a point for that and a point for the final answer. So this was a 3-pointer. Now, we're on to beaker 3, our salt. Now, remember when it dissolved, it left that weak conjugate acid in solution. Weak conjugate acids can also react with water and set up a K, an equilibrium system. Now, if we know Kb for our base, we can get at Ka for the conjugate. So remember that. If you know a Kb, you can find the conjugate Ka. If you know a Ka, you can find the conjugate Kb. So all they're asking for here, there's not a fancy rice that's being requested. All we're trying to find out is whether you brilliant chemists have learned that there is a straightforward relationship between the Ka and Kb of conjugate pairs. And that is equal to 5.6 times 10 to the minus 10. Okay. Now we're adding volume to volume. This is going to be a little trickier. So we're adding beaker 2 to beaker 3. So we have a dilution this time. And we have to address that dilution before we can get to a pH. Now, there is a simple way to do that. I want you to do the calculation for dilution because I want you to always remember that. But if you'll notice, both of them, my NH3 is equal to my NH4 because they have the same volume and same molarity. Right? So, and it asks us to calculate the pH of the resulting solution. I'm going to go ahead and calculate those concentrations. This is a little longer than needed, but I hope you will understand it a little better when all is said and done. So I have 0.100 is the molarity for both. The volume for both, each of the beakers, it was said at the beginning, is 25 milliliters. So that's sorry, not 0.2. We don't have to change it if we don't want to on a boom boom, right? As long as the volumes are the same on both sides. Now, when we added them together, when a question says assume the volumes are additive, that just means that 25 plus 25 did give me 50. There are times when there are attractive and repulsive forces, and that you would not get exactly those volumes. So that's why that statement is made. So now both of these are 0.05 molar solutions. Okay. Now we have to then plug this into rice. So these are equal to one another. And you can do this a couple of ways. I'm going to go ahead and set it up in this formula because I have that already. So Ka is equal to my H3O plus. That's the same as H plus. Remember symbolic synonyms. And NH3 over my NH4 plus. Okay. Now those are equal. That's why you didn't really have to do fully the calculation. If you had stated that they were equal, you would have been okay. I think it's better for you to remember DSE. Doc saves everyone. Dilution, stoichiometry, equilibrium. Okay, so that means my Ka is equal to my H3O plus, and that's 5.6 times 10 to the minus 10. And hopefully you can predict that your pH is 9 point something. Now you'll have your calculators here. They did ask you to calculate it. And I get 9.25. on this. Now, honestly, that's what the AP had as well, and it's probably because they used 2 sig figs from the Ka values and the Kb values. Now, those of you who are Henderson-Hasselbach fans, not David Hasselhoff, Henderson-Hasselbach, could have seen that pH is pKa plus the log of my ammonia over the acid, and you could have done a similar, just as long as you'd used the correct Ks if you'd treated it as an ammonia problem. Well, these were equal to one another, so those are 1. The log of 1 is 0, so that cancels. pH is equal to pKa. Take minus the log of pKa, which is what we did here, and you still get 9.25. Okay, let's go on. This was actually a very long problem, in my opinion. This one says the contents of beaker 1 are poured into the solution made in part C, and the resulting solution is stirred. Now, is the resulting solution an effective buffer? Okay, that's your first question. Well, remember, we had a concentration of NH3 equal to our NH4 plus, and those were both equal to 0.05 molar solution at that point. Okay, now this was a buffer solution. That's why we could use the Henderson-Hasselbach equation. That was a buffer solution. Now if we add H+, the H+ or the H3O+ is going to react with the NH3, and that's going to make NH4+ in this case, okay? So we'd have H3O, NH3+, and it'll make water is our remaining. If you put just H+ there, you would not have got this wrong. This is 0.0, well, we have a dilution, right? So we really do, if you want to be thorough, have to dilute this. But I hope you see, one way or another, this is starting at 0.05. This is starting at 0.1. So let's go ahead and do the dilution just so you can clearly see and understand what I'm talking about. So this was 25 mLs times 0.1. My new volume is 75 milliliters times my new molarity. I'm hoping that you see that one way or another, this one's going to be an excess, and this is going to be our limiting. In other words, the ammonia is going to run out. I am going to prove that with numbers in this case. So 25 times 0.1 divided by 75 gives me 0.0333 for my H3O+. Now, for my ammonia, I had 50 milliliters, remember, of 0.05. And actually, these might be 1-to-1 if I look at it, once I get my numbers calculated here, times the new molarity. So I get 50 times 0.05 divided by 75, and they are. Actually, it wasn't even an excess, but it was 1-to-1. Okay? So this is going to go to 0. This is going to go to 0. I already had a volume of this. I'm going to add more to that. But the net is I had a buffer with NH3 and NH4+. If I have both, it's a buffer. I no longer have any ammonia. I have to have both pairs for it to remain a buffer. So the net answer is not a buffer anymore. We're missing one of the pairs of our weak base conjugate acid or conjugate base acid pair on that. So this is not a buffer. Okay. Now, this goes on because apparently this was not long enough of a problem. This goes on to ask us what the ammonium ion is for this. So let me delete this here. It's kind of fun when you do that. Okay, start fresh with a fresh slate. And it says calculate that final ammonia in the final solution. Okay, so what we're going to do is get at our final molarities in this case. And we just determined, let's see what we had. Let's just do our, I'm not going to do it the way AP did it. They did it in forms of moles, and I think that you'll be okay with this better. Just based on what we've done in class, I think this is going to make more sense. You can look at the AP question later if you want. I'm just going to do H plus here and NH3, all right, because we poured those beakers together. We've already determined that this was 0.0333 molar. This was 0.0333 molar. All right, it's going to go to ammonium. Let's go ahead and look what the ammonium would be. Well, the ammonium, once we diluted it again, right, it should be the same as my initial ammonia, but I'll prove it to you. We had 50 mLs of it, and it was 0.05, and it's the same calculation that we did for ammonia because they were the same initial, 75 times my new molarity. Okay, and this is also 0.0333. Right? Now this is a stoichiometry. That's our start. We're going to do our shift, and we're going to do our stop. No equilibrium here in this particular part of it. These are 1-to-1. There's not a limiting, even though I guessed that. I guessed wrong. That's why I like to use numbers myself. That goes to 0. That's plus 0.0333. And that's plus 0.666. Or honestly, once there was rounding, it was 0.667. Whoops, I missed my 0 there. Sorry about that. And that's it. That is my final molarity of NH4+, which is what the question asked for. And we're done. So if you wanted to, I've got it worked out the way I would normally work problems out, which is a little different from the AP key, but you'd still get lots and lots and lots of points as long as you remember DSE. Doc saves everyone. See you in class. Until then, this is signing off.